just going to get it up. There you go.
Senior professor can't operate PowerPoint. Awesome start. So the next award is the Yenstch-Schindler Award, and this is the Early Career Award for somebody that's within 12 years of their PhD. This is actually one of the most popular awards. It just started a year ago, and our inaugural winner was Emily Bernhardt, and her work on contributions to stream biogeochemistry and how she managed to balance science with policy, have an effect on people, both positively through education, but also societally through her work. This year's, well, you'd think that was a pretty hard task to follow, and it is, but this year's winner, I think, is equally talented. Andy Pershing is the 2014 Yenstch-Schindler Early Career Award winner. Andy's background is an honors degree from Brown and a PhD in 2001 from Cornell, and his research looks at climate change and reciprocal interactions between the biophysical world and the human world, so coupled systems they've been called, and takes a particularly quantitative view of this. And bringing quantitative science to this kind of interaction between the two spheres, I think, is really important. Often models are viewed as only as good as your insights on the system. And I think the thing about Andy's work, which is so transformative, is his insights are brilliant and his models basically are right. So they'll help us understand the organization of ocean systems, and in doing so, help us understand how the world works. So Andy's award is not just for the science, though, it's also for leadership. He's been involved in the 2012 congressional hearings. He's pretty much the leader on any project that he gets involved in, not elbows out, I've got to take it, it's mine, but collaborative leadership to try and achieve something important. So I think with that, Andy brings the best qualities that we'd like to see in all our aquatic scientists. And with that, I'd like you to welcome Andrew to the stage for his award and his presentation.
All right, thank you, Peter. Thanks, everybody. This is really an exciting honor. To get this from ASLO is very special. It's an organization that's meant a lot to me throughout my career. And to have the connection to Charlie Yentsch is also incredibly special to me, both because he's a towering figure in oceanography, but also because of the influence he's had on the marine science community in the state of Maine, where I'm now working. So I'm going to start, actually I'm not going to start, I'm going to start with a very quick, if I can figure out how to work. There we go. All right, I'm going to start with a very quick acknowledgement of some of the people who've supported me throughout my career, starting on the top left with my family, who has always been there, who has never gotten up from the table when I've gone on a rant about climate change or waxed poetic about the virtues of MATLAB. The three institutions where I've worked have been incredibly influential in helping shape and direct my career in sometimes subtle and nonlinear ways. I also forgot to put the logos up here for the funding agencies that have supported me throughout my career, but notably NSF, NASA, and NOAA, as well as the Lenfest Ocean Foundation. But finally, I've been incredibly fortunate in the people that I've gotten to work with, starting with Chuck Green and Bruce Monger at Cornell University, and working to many of the people you see on the screen, notably Nick Record, Kathy Mills, Fred Mapps, and lots of other people who really make this very challenging process that we call science lots and lots of fun. Because as we all know, the fun is key because of we don't do it for the money. Okay, so I'm going to start with a quick overview of my talk, and I'm going to be giving just a little bit of a recap. In many ways, this is sort of a look back on some of the work that I've done, but also trying to draw some synthesis together, and in many ways trying to simplify some of the views that I've had of the ocean. So I'm going to start by talking a little bit about the changes that we expect in the North Atlantic. I'll then talk about some of the observations that we've made about the plankton communities in the Northwest Atlantic, and then consider a couple of different physical drivers, and then talk about the implications of those physical drivers. So everybody's aware, I'm sure, of the climate projections that we expect that by the end of the century we'll be 3 to 4, maybe even more degrees warmer than we are right now, that we'll have an Arctic that's devoid of sea ice in the summer in maybe 30 years or so. But that, if you look at these projections, if you look at the detailed spatial projections, one of the things that really comes out is how the impact of global climate change is much stronger at higher latitudes. So we see at the high latitude systems that in the upper right, you see that at high latitudes in the northern hemisphere, that the warming is even more intense. The panel below shows the precipitation change, and we expect to see an increase in precipitation at high latitudes. And so all of this is going to combine to make the North Atlantic much fresher and much warmer than it is right now. And what I'm going to do today is trying to convince you that warming and freshening are really two sides of the same coin, and that both are going to lead to very similar impacts on the marine ecosystems in the North Atlantic. And so my overriding question for today is, how do ecosystems respond to changes in temperature and salinity? And this basic question of how physical drivers impact ecosystems and structure planktonic ecosystems has been at the heart of the work that I've done throughout my career. So if we want to look at an ecosystem, we need a record of change. We need to be able to collect some data. Thankfully, we have this guy, this very dapper fellow. This is Sir Alister Hardy in the 1930s with his prize piece of 1930s technology, the continuous plankton recorder, the clockwork plankton sampler. It's probably one of the worst ways of sampling plankton, but the great thing about about the Hardy plankton recorder is that people have been using this consistently terrible way of sampling plankton in consistently the same way since the late 1950s. And so it gives us this really great record of change over an amazingly large area across the North Atlantic. And even now it's expanded into other areas like the Southern Ocean. So in our region, the continuous plankton recorder lines have been operated by the Sir Alister Hardy Foundation, and then the two in U.S. waters are operated by the National Marine Fisheries Service. And I'm going to focus on 4 regions, going from the lower left to the upper right, the Gulf of Maine, near where I live, to the western Scotian Shelf and the eastern Scotian Shelf, and are just upstream of us in Canada, and then up into a large region in the North Atlantic that I'm going to refer to as the Labrador Sea. It's really the southern Labrador Sea, North Atlantic current region. So across those regions, we have a similar assemblage of species. There's some differences as you move into the coastal waters, as you move into the oceanic waters. And what I did was I selected a subset of the taxa that are consistently sampled by the CPR and that are represented throughout the range that I'm considering. So the blue guys in the middle are the copepods. These are primarily herbivorous or microcarnivorous. We have Oithona on the left, which is the smallest one, moving over to the right to Calanus finmarchicus, which is our large lipid-rich copepod that's really at the center of the North Atlantic food chain. Up above them, we have 2 predators, or groups of predators, chaetognaths, and then the predatory copepod Perieuchida norvegica. And then below them, we have 2 broad groups of phytoplankton, broadly dinoflagellates and diatoms. So what I did was to try to make a sense of all of this variability was I threw these time series into a principal component analysis. And I did the principal component analysis for each region independently. And what emerged was a common pattern of variability that we see in all of these regions. And at the heart, that pattern of variability contrasts the small copepods and the phytoplankton against Calanus finmarchicus. So Calanus stands alone as the blue bar that's pointing down in all of those graphs. And on the Scotian Shelf, Metridia is kind of an interesting species. It goes back and forth. It's fairly large. It's almost as large as Calanus. And in the Labrador Sea and the Gulf of Maine, it seems to act like a small copepod. On the Western Scotian Shelf, it acts a lot like Calanus, at least in terms of this principal component analysis. So, of course, with every principal component, there's an implicit time series behind it. And if we look at the time series for the 4 regions, some patterns emerge. And I'm not going to go into this in any detail, but I do want to highlight 2 things. On the top panel is the time series from the Labrador Sea. And you'll see that there's a rather persistent trend beginning around 1990 and continuing on through 2010, which is when the time series stops. And then in the Gulf of Maine is really, really weird. And that the Gulf of Maine goes through this very regime shift-like pattern of low in the 80s to high in the 90s to low in the 2000s. And on all of these graphs, high indicates conditions which are favorable to those small copepods and more dinoflagellates. A low value indicates conditions that are where Calanus is dominating. Now, with all of these regions, the question, of course, is what's driving this variability? Even though there's very little correlation among these time series, there's a little bit of one between the Scotian Shelf and the Gulf of Maine. But through these time series, the question is there any common driver? So for all of these, I just did a very simple correlation where I assembled some hydrographic data from each of these regions and began correlating the temperature and the salinity with the variability patterns coming from that, associated with that first principal component mode. And in the North Atlantic and the Labrador Sea, we see that temperature is the main driver. We have very strong positive correlations. So warm temperatures indicate a shift towards those smaller copepods and towards more dinoflagellates and diatoms. Colder conditions indicate a shift towards Calanus. In the eastern and western Scotian shelves, we have a very similar pattern where freshening, fresh water, tends to drive us towards that small copepod community. And in the Gulf of Maine, we also have fresh water and low densities that are, indicators of that small copepod community. Now, what all of these things have in common, whether it's fresh water or whether it's warm water, is that both of them are light. So in all of these cases, what we're seeing is that as any process that tends to lighten the water, that tends to increase stratification, causes us to shift towards that community of smaller species and more diatoms and dinoflagellates. So similar forcing gives us a similar pattern. So I want to talk just a little bit about what we think is driving these responses. We think that there has to be some sort of forcing on the phytoplankton, probably through reduced light limitation associated with increased stratification. That then leads to positive correlations moving up the left-hand side of the graph. But that we also think there probably has to be some independent physical forcing on Calanus. And that could be as simple as just a habitat association, that Calanus has a preference for cold, salty water, well-mixed conditions, but it could also be related to changes in the phytoplankton blooms. Another thing I want to point out, and then I'll try to wrap up here very quickly, is that in the Gulf of Maine, things get a little bit more interesting in that we have the emergence of this negative correlation between Chaetognathes, one of our predators, and Calanus. And what this creates is the potential for a positive feedback loop, where if we were to have an increase in diatoms for some reason, that could propagate up the food chain on the left, that could lead to increased Chaetognathes, which could then drive Calanus down, and because Calanus is potentially a grazer on the phytoplankton, it could allow the phytoplankton to increase further. So we end up with the potential of a positive feedback loop, which might explain why we see that regime shift-like change in the Gulf of Maine. So just very quickly, some implications. We think this is potentially going to impact cod. We've seen that in the Gulf of Maine when we see conditions that shift away from Calanus and towards the smaller copepods, that we have lower survival of juvenile cod. We think it's going to impact salmon. When we have the smaller copepod community and warmer water, we have lower productivity among all of the Atlantic salmon stocks in the Western Atlantic. And we also think it might have an impact on the North Atlantic carbon sink. That's through the production of fecal pellets, because Calanus is our largest copepod species. It can be very abundant at times, and it makes really, really large poop. And really large poop sinks and takes a lot of carbon with it to depth. And that's my graduate student Karen Stamieszkin's thesis project. So just to wrap up, we've seen widespread ecosystem changes in the Northwest Atlantic. And even though the forcing is different across these regions, we see the same response to the same kind of forcing. That is, if we see an increase in anything that's associated with stratification, we get an increase in phytoplankton, an increase in small copepods, and decreased Calanus. We think that that's potentially associated, that these changes are explained by the physics, but then with the biology then modifying that, so with the Chaetognathes offering this potential for feedback. And then finally, we're very interested in what the future might mean and how this might impact marine ecosystems. And there's a really interesting opportunity to test this by taking advantage of the fact that the North Atlantic, and in particular the Gulf of Maine, is warming faster than 99% of the planet at the moment. So thank you very much. I really appreciate this.
Folks, you can meet all of today's speakers at the ASLO Expo in room 251 just after this session. So if you've got questions on that and you want to speak with the speakers, please do so. If I can have, okay, I'll let you do it.
You just let me do it.
I'll just not screw it up.
It's just better this way. Okay.
That's what my students say.
Okay, so help me.
So it's intro.
Oh, we have intro back there?
Okay, so then it'd be Martin.